Okay, chemistry 2 time. We're talking about acids and bases. What's an acid? It's kind of a trick question. Why is it kind of a trick question? That's kind of a trick question. No, but why is it a trick question? No. Well, why is it a trick question? If I ask you to define acids and bases, why is that a trick question? Yeah, there are 3 definitions that I'm aware of, or that your book is just... oh, this is chapter 18.
There's no definition.
Oh, yes, there are. You mean...
There's no, like, just acid is...
Yeah, there are 3 definitions of acids and bases. We have the Arrhenius definition, the Bronsted-Lowry definition, that's how we say it, and the Lewis definition. We're going to have a definition for acids and bases in each of these definitiones. In the Arrhenius definition, what is an acid?
Isn't it like something that...
Yep, that contains hydrogen ions that ionize in aqueous solution. And what's a base in the Arrhenius definition? Well, just use this as a guide. If an acid is one that releases a hydrogen ion into solution, what is a base? One that releases a hydroxide ion.
It's releasing, it's not containing.
It's releasing. In both of these cases, it's releasing a hydrogen ion. But I said that was going to happen. Bronsted-Lowry definition, for an acid, it's almost exactly the same, but we could say it's a proton donor, and a base is a proton acceptor. Do you understand how this is a broader definition than this? Like, basically, it's kind of like squares and rectangles. Like, all Arrhenius definition bases are also Bronsted-Lowry definition bases, but not all Bronsted-Lowry definition bases are Arrhenius definition bases. And then in a Lewis acid and base, it is all about the electron pair. Electron pair acceptor is an acid, and electron pair donor is a base. And this is the broadest definition of all. The things like, when we talk about, well, for instance, your blood being basic, I think is what you found in your lab, or should have found in your lab, or your saliva being acidic, those things are probably the Lewis definition of acids and base. The blood certainly does not contain a hydroxide group freely floating around in it. It may or may not be a proton acceptor, I don't actually know, but it's definitely a Lewis base, the blood is. So this is in order, as we organize this chart. Is this, how should I say it? Does this encompass more substances as we go from the Arrhenius to the Lewis definition, or fewer?
Fewer.
Well, let's try again. Yeah, more. More encompassing. More, as I had said before.
I thought it goes from
More.
broad to more specific.
It's most specific to broadest, in this order at least. Maybe your book gave it in the opposite order, but in this order at least, this is the most specific definition. Basically, all these are these, and all these are these, but not the other direction. What are some physical properties of these things? Well, let's start a different thing. I'll use a different font so we can tell we're talking about a different thing. Physical properties. How could I tell properties? What an idiot. Gosh, this guy should not even have a job. Properties. physical properties have positive self-talk. Hey, you jerk. It's just some negative self-view with that. It's not self-talk if I say it to you. That's just people talking. That's just talk. It's not self-talk. God bless you. God bless you. So physical properties. Well, how could I tell an acid or looking at them? But what are some things I could do? What are some physical properties that acids and bases have? Let's start with acids. What are some physical properties of acids? Not good enough. Acidic. Well, let's think of some acids that we commonly have experience with, and let's think of what are some properties they have. What are some common acids that we found? Saliva was a mild acid. What else? From your lab, what were some other acids? Hydrochloric acid. Yes, you probably don't have very much experience with it. It lives inside your tummy. It doesn't live at all, but that's what your stomach acid is hydrochloric acid. Not always. What are the common acids that you have in your house, in your kitchen? Probably your kitchen, maybe even in your cup, depending on whether or not you brought only pure water into this class. What's one of the acids that Dally drinks every day, or I thought she did?
Tea.
That's not an acid. Lime juice, lemon juice, vinegar. What are some physical properties of acids based on that?
Sour.
Sour, yeah, they taste sour. We don't want to taste them, especially in the laboratory. But if you were to taste them, they taste sour. Bases taste bitter. Bases taste bitter. Bases themselves don't have a taste. The reason they taste better and they feel slippery, especially strong bases, is not because those are the properties of these actual bases, although we're including them in properties of the bases, but the reason those your body by making your flesh into soap. Remember we talked about this at the beginning of the year. That bases turn fat into soap. That's why people buy strong bases part of the time, to make soap. But soap tastes bitter and soap feels slippery, and so when a base interacts with your flesh, these two things happen. But acids, I guess to some extent you could say that the acids are sour because they're interacting with your taste buds too, but your body has been designed to detect the presence of acids, specifically ascorbic acid, scurvy. That's why you like the taste of sour. That's why Warhead is popular, is because your body is designed to make it so that you like that taste because you don't get scurvy if you like it. And then if you don't get scurvy, your teeth don't fall out and you don't die of starvation. Or your organs don't rupture and you die in a puddle of blood. Anyway, those are the symptoms of scurvy. But anyway, what are some other physical properties of acids or bases? Well, what did you find in your lab? What was the physical property of acids and bases in your lab? What did it do to your litmus paper?
Oh.
Generally, the acids turned it redder. Yeah, redder litmus paper. And the bases turned it, I think the universal indicator we used was green. Your book says blue. It depends on what you've used, but we're going to put bluer. I would say green is bluer than red. Conjugate acids and bases. Remember that for something to be an acid or a base, it must be an aqueous solution, so it must be combined with water. So for instance, if we had hydrochloric acid, it's not hydrochloric acid, it's just hydrogen chloride, a gas, what we call an anhydride. But we have hydrogen chloride, and it combines with water. You remember this is a reversible reaction, to some extent at least. For weak acids, it is in equilibrium, but in strong acids, it really does just completely be taken apart. It does equilibrium anyway. But what does this become? Do you remember? Yeah, it is, but it's not H2Cl. The hydrogen is gifted.
So it's Cl plus H
Yeah, it's Cl minus plus H3O plus. And by the way, what's his name? Do you remember? You have to remember his name.
Oh.
Uh-oh, you have to remember his name. It's hydronium. This is very important in this case. Hydronium. This is the hydronium ion, H3O plus. What's the acid here? Well, that's the easiest question. What's the acid? Yeah, HCl is the acid. What's acting as the base?
H2O.
Yeah, water is acting as a base. So what do we call Cl minus? You remember this part? We did this. This is the conjugate base.
Oh, base.
And this is the conjugate acid. Let me read you the book's definition of those things so that we can remember them better. A conjugate acid is a species produced when a base accepts a hydrogen ion. A conjugate base is the species that results when an acid donates a hydrogen ion. So whatever's left of the acid after it has donated its proton, its hydrogen ion, is the conjugate base. And whatever is left after the base has accepted the proton is the conjugate acid. Conjugate means that they have come together. So the base having come together with the base having come together with an acid produces the conjugate base, which is the remains of the acid. Think of the acid after it has donated its proton, and the conjugate acid, which is remains of the base after it has accepted the proton. We're using this definition for this. The Bronsted-Lowry definition goes with conjugate acid and base. Your book also talks about the idea of monoprotic and polyprotic acid. Monoprotic just means it only has one hydrogen ion to give, and polyprotic means that it has many. And that does not necessarily do the strength of the acid, it's just the way it is. So a monoprotic acid has one hydrogen ion, like HCl. This is a monoprotic acid. Whereas if we had, like, for instance, H2SO4, that would be a polyprotic acid. Only has one hydrogen ion to give. And that's a distinction that we have to make because, for instance, if we look at acetic acid, which is vinegar, HC2H3O2, the reason we write it this way, it would be acceptable to write it like this. They're the same, they mean the same thing. But the reason we write it like this is because it helps us to remember that only this hydrogen can be donated. So this is still a monoprotic acid, because only this hydrogen can be donated. This acetate polyatomic ion is all one lump. It has to stay together.
Polyprotic is just more than one.
Polyprotic means there's more than one proton. That's why the suffix is protic, because it's referring to the protons. Which remember that a proton is just a hydrogen ion.
Proton to give?
Yep,
Hydrogen ion.
same thing. Your book then makes a distinction between strong acids and bases and weak acids and bases. The difference is the strong acids and bases fully ionize. They become this. We could even, and we usually do, write this just as an arrow. 100% of this becomes these two things. That's a strong acid. The whole thing ionizes. In a weak acid or base, it only partially ionizes. Only some of these become the conjugate acid and base. This is a weak acid, and so we would write it like this. Get out of here, Lewis. Tack the H2O on over here. This is usually, the equilibrium symbol is usually what we use to represent that a weak ionization has occurred, which means that not all of this has broken up into this. It goes back and forth. There's always some of both. There's always some reactants and some products. What? Clear over here? Here? Oh, heavens. From 9 minutes ago? More encompassing. Like there's more things, more species are included the further we go down this list. So just like we had KEQs, we now have Ka and Kb. And since we already did the work to understand what KEQ is, Ka and Kb are going to be pretty easy. So Ka is for an acid, and Kb is for a base. And all it is the concentration of the products raised to whatever power of their coefficients over the reactants, same thing to the whatever power they had. And same thing with the Kb, except now we would be doing it with a base. But it is set up and analyzed the same way as KEQ, including we include the acid itself. We don't include water in the Ka or Kb. So we would include the acid, we would include the conjugate base, and we would include the conjugate acid. Let me make sure that last one is true. Yeah, we do. And X and Y are coefficients in the chemical formula. I'm sorry, in the balanced chemical reaction. X and Y are coefficients in the balanced equation. So it's set up the same way as KEQ, which we've already done. And if you need a refresher, you can watch the video about that. Your book also talks about an ionization constant, which is the collective term for both of these. So Ka is the acid ionization constant, and Kb is the base ionization constant. Your book also talks about Kw, Colby-Welling. Never mind. And Kw is the concentration of hydrogen ions times the concentration of hydroxide ions. What do you think the W stands for? Why, Ethan? What do you think the W stands for here in Kw? Well, if we had Ka for acid and Kb for base, what's Kw probably? And look at what we've got here, only hydrogen and hydroxide. Well, there must have been a reactant, so what must have leave out? What do we leave out of this? What do we always leave out of our KEQs? Water. So what does W probably stand for? Water. If the only reactant was water, and the products were hydrogen and hydroxide, Kw stands for water. Neutralization principle, this can shift left to H2O or right to H plus and OH minus, depending on the conditions, in the same way that all the other KEQs we had talked about can shift according to Le Chatelier's principle. The final relate directly to Kw, which is pH, the penultimate, the second to final thing, because we still have one thing to talk about, which is pH and pOH. And this is about the easiest math we'll do all year. pH, it's always capital H and lowercase p, not in that order. Capital P, lowercase p, capital H, and then lowercase p, capital OH. This stands for the potency of hydrogen ion or the potency of hydroxide ion, which just means how many of those could potentially be generated in solution. And the equation for both of them is negative log of the concentration of the respective thing. So negative log of H plus for hydrogen and OH minus for hydroxide. Do you see how these two things fit together with these three things? Would it be possible, and I guess with all of this really, but would it be possible for us to find the pH if we had already found Ka? Yeah, because we would have hydrogen or hydroxide, and we could use that concentration. So even if we just had the concentration of the acid itself, we can find the pH by going from the concentration of the acid to Ka, and then from Ka to pH. Because the products will always include, for an acid, the hydrogen ion, or hydronium ion. It doesn't really matter how we describe hydrogen ion or hydronium ion. And then your book has an even more simple equation for how, it's even titled, How pH and pOH are related. This is it. That's it. That's the equation. pH plus pOH is 14. For any given substance, pH plus pOH is 14. So,
P stands for potency, which means what?
like how much they can potentially generate. How much there could be if they fully ionized. Or ionized to the best of their ability, I should say. So if I find that the pH of a certain solution is 3, what is the pOH? 11. Yeah, this is idiot level math. If I find that the pOH of something is 1, what's the pH? Did you say 13? Good, because that's right. That's the right way. If something, yeah. We usually, even for bases, we usually use pH. So you can calculate pOH using your KB. You could calculate pOH, and then you just subtract whatever your answer was from 14 to get pH. Because we usually, pH is the more commonly used, certainly, of the two. Although you could do it both ways. You could go either from pH to pOH or pOH to pH. And the last thing is the idea of neutralization. What's neutralization mean? Well, what's the suffix ization mean? Like if I was going to dallyize something, what would it mean for you if I dallyiized the classroom? Yeah, it's becoming that thing. It's becoming at least more like it. If I dallyize my classroom, it would look like the inside of a Chrysler 200, 2015. Leopard print everything, probably, I assume. Cow manure. Anyway, but if I were to neutralize, it's becoming more. Yeah. Make neutral. How would we neutralize an acid? At a base. Especially in the Arrhenius definition, because if any acid we have must have the hydrogen ion, any base we have must have the hydroxide ion, so it's always going to be in this form. HX plus MOH yields MX plus HOH. That's how it always is in the Arrhenius definition. So what two things are produced when an Arrhenius acid and an Arrhenius base combine? What two things are produced when an Arrhenius acid and an Arrhenius base combine? No. What's this? Yeah, water. So water is always produced, and what will this be left? Well, we had a metal, and what am I using M here to represent metal? And what's the X represent? What must this have been for this to be a Arrhenius acid? Yeah, but what must the X have been? Some, what do we call, had to be hydrogen anion, some anion. Usually a halogen or a polyatomic ion, but either way it doesn't matter. A metal and an anion combined makes an ionic compound, specifically a salt. So it always produces. Do I mean it always produces sodium chloride? No. A salt means that it's an ionically bonded substance. So it could be calcium sulfate. It could be cobalt 2 chloride, which is carcinogenic. Just because it's salt doesn't mean that you can spread it on your You know how you do with salt. You're always like, spread me some salt, Mom. That's how you talk to your mom. But just because it's salt doesn't mean it's edible. Yeah, this is some anion. But that ionic compound is a salt. And like I say, cobalt 2 chloride, we use that in the lab. Cobalt 2 chloride, remember, we had to take extra precautions because it's a known carcinogen. So cobalt chloride would be a salt that could be produced if we had, for instance, hydrochloric acid and cobalt hydroxide, which probably doesn't even exist because I think it's insoluble. But if we mix those together, it would make cobalt chloride and water. So in theory, and this is the fun thing that I'm going to leave you with, in theory, if we have hydrochloric acid, even concentrated hydrochloric acid, as concentrated as it can get, 12 molar, I believe, hydrochloric acid, plus as concentrated as it can get, sodium hydroxide, which is lye, drain cleaner, the thing that if you get in your eyes or on your hands, you're ruined forever. Hydrochloric acid plus concentrated sodium hydroxide, which is actually a solid. What would we get from that? Well, a ton of heat for one thing, but also, well, do the little, what would be produced here?
Salt.
Yeah, well, you mean table salt plus water. So in theory, if you had the stoichiometric ratios exactly correct, and all your metrics were perfect, and these were pure substances, and you mix this terribly dangerous fuming hydrochloric acid that would burn a hole in you if it touched you, and this would turn you literally into soap if it touched you, and you mix those together in the exact right ratio and they're perfectly pure, you would be able to drink the result. It's just salt water. You could boil your spaghetti in the result. We're not going to do that. But what we did do in the lab, one of my reagents was off. In fact, I know one of my reagents was off. But we did this one year, and we tested the pH expecting it to be 7, because that's what it should be. If it's just water, it should just be 7. And then we could have drank it. We'd never drink anything in the lab, especially this. But the pH was not 7. It was like 3, and it was not good. So we didn't drink it, and we never would have anyway. Bye.